Welcome back to CMOS RF integrated circuits. In this lecture, we are going to discuss the dynamics of a phase lock loop, and then we are going to move on to study about integer n frequency synthesis. So, in the last lecture, we were talking about a phase lock loop. So, I had built up a phase lock loop in general, how a reasonable topology of a phase lock loop looks like. So, we had built a phase detector, we went into the complete circuit for the phase detector. There will be 2 flip flops, AND gate, clear, etc., state machine diagram and so on. The phase detector generates 2 signals, which are basically 2 bits of a 2-bit binary code. Binary code is for +1, -1 or 0, right. So, these 2 bits are called up and down, and then we have some sort of a current steering DAC. I am going to call it a current steering DAC. If you look up the books, it is called a charge pump, and this digital value is converted to an analog representation over a capacitor. Now, if I just use a plain capacitor, then unfortunately the system becomes unstable, because there will be 2 integrators in a loop and I can't do that. So, instead we have this combination of capacitor and a resistor capacitor series, right, and this particular impedance will have a pole at DC. It will also have a 0 and another pole. So, that is basically the idea, and this voltage is used to control the VCO, the voltage controlled oscillator. Now, this is a phase lock loop in general. We said that our analysis works only when the loop bandwidth is some fraction of the oscillation frequency, something like 1/10 of the oscillation frequency. So, that is when the phase lock loop really is going to work. Now, unfortunately, we want as large a loop bandwidth as possible, which means that I want exactly that much loop bandwidth, which gives me I want exactly the maximum amount of loop bandwidth, where the dynamic still works according to our mathematical model of the phase lock loop. Okay. And the reason why is because I want the VCO to have the phase noise properties of the reference oscillator. Okay. So, what have we achieved with this? If the reference oscillator is oscillating perfectly at 1 gigahertz with 10 ppm of variation, then the local oscillator, the voltage controlled oscillator, is also going to oscillate exactly at 1 gigahertz with 10 ppm of variation. So, I have got accuracy. What else have I got? Accuracy in terms of a number, what exactly is the frequency. I have also got spectral purity. Okay, within the bandwidth, within the loop bandwidth, I have got spectral purity. Outside the bandwidth of the phase lock loop, the voltage controlled oscillator does whatever it wants to do, but within the bandwidth, the phase is controlled by the reference phase. The reference phase is being tracked. So, the phase of the voltage controlled oscillator is equal to the reference phase, right. So, you have got spectral purity over there. So, these are the 2 things that we have achieved. We have not achieved any kind of agility so far. Fine. Now, before I move on to the next part, I want to kind of understand what is going on. First of all, does frequency does phase lock also mean that the oscillators will have the same frequency? Yes. So, what I am saying is that phi out is equal to phi ref. If phi out is equal to phi ref, does that mean that the derivative of phi out, that is the frequency, is equal to the derivative of phi ref, that is the frequency of the reference? Absolutely, there should be no mistake in that. Okay. That is great news. So, you get a perfect frequency synchronization, you get phase synchronization. Next question is, will this always work? What if my voltage controlled oscillator is unable to generate such a frequency? Or what if the voltage controlled oscillator is able to generate such a frequency with great difficulty? So, the answer to all this is something called lock range. So, phase lock loop has a lot of these properties. Lock range is one of them. Okay. So, the voltage controlled oscillator has a certain center frequency, free running, that is the frequency that it is going to oscillate at, and if the reference frequency is anything within the lock range of that. So, if the reference frequency is out here, then the voltage controlled oscillator will be able to lock to that reference frequency. Okay. So, there are a lot of these properties of phase lock loops. Now, we do not want to get into all of these details. I really want to move on to the next topic, but this is of some interest because you want to make sure that when you have made your voltage controlled oscillator over the entire range of process corner variations, etc., the reference falls within the lock range of your standalone oscillator, around within the lock range centered around the free running oscillator, right. So, you want to make sure of that. Okay. What else? Next thing is, how much time does it take to settle? So, if you build a phase lock loop and you switch it on, you switch on your reference frequency all of a sudden, then the phase lock loop is going to try to lock. Now, if I plot the control voltage to the VCO as a function of time, maybe this is the control voltage that is suitable for frequency lock. Okay. For frequency lock, this is the control voltage, that is the correct one. You start it off, let us say initially the control voltage is over here when you start it off, or maybe it is at 0 volts, maybe let us say it is over there. So, what is going to happen is, depending on the transfer function. So, you have got a lot of these poles, zeros, etc. Right. What is going to happen is this voltage is going to try to reach the target. Okay. It could go in that fashion, it could also go in a different fashion, it could do something like this. Okay. Or if you have not paid attention to the values of the resistors and capacitors, then it might not even settle ever, in which case it is going to go like this. Right. So, all of these are possible. These are all dependent on what are the resistors, capacitors that you have chosen over there, how exactly you have built the loop, what is the precise transfer function, where are the poles and the zeros, what is the damping factor. We like damping factors of something like square root of 2. Okay. So, you need to read up all of this in your control theory book, velocity control. You can also read up all of this in a book which has a chapter on phase lock loops, dedicated to phase lock loops, how exactly to choose the damping factor, how to choose the resistor value and the capacitor value, etc. Right. But we are not going to go into too much detail as far as this is concerned. Now, settling time, is this something of great importance? It is. It is something of utmost importance, because if your base station asks you to go to this frequency now, it is going to give you a certain amount of time to reach there, okay. And your settling time, you have to reach there, that particular frequency, within that time allocated to you, right. So, you have to worry about it. Now, definition of settling time, etc., is of no concern. What you are really finally trying to do is achieve oscillations with a certain amount of jitter or certain amount of phase noise. So, you want to reach your target value with a certain amount of accuracy. So, that will decide how much time it has taken for you to reach the target frequency. Okay. Now, the next thing is, what does this settling time depend on? Do you think the settling time will be more if the bandwidth is less, or the settling time will be more if the bandwidth is more, the loop bandwidth? What do you think? Does this settling time have anything to do with the loop bandwidth at all? This loop bandwidth. The settling time will be less if the loop bandwidth is more. Settling time will be more if the loop bandwidth is less. Why? Because if I put an impulse, think about it over here. Okay. If I put some sort of so phi ref is a ramp, but suppose I have a step on top of the ramp. Okay. Wherever the step is, there are extremely high frequencies at that point of time. So, there are high frequency components. Now, your control system has to track these high frequency components. If it has infinite bandwidth, then the output also will look exactly like that. But unfortunately, you can't build your control system with infinite bandwidth. We have some restrictions, right. So, that means only certain components, up to certain components can go through, fine, which means that your phi out is going to try to behave like that, but unfortunately because some high frequencies are blocked out by the loop, it is not going to be able to mimic exactly what phi ref is doing. All right. So, this is basically the idea. Okay. The larger the loop bandwidth, the better phi out is going to look in relation to phi ref, okay, which means that the settling is going to become faster. If you block out most of the high frequency components, then your system is going to slow down, and as a result the loop is going to stabilize with a much larger settling time. All right. Now, let us move on, right. Is it conceivable this is my phase detector, right. So, this is the normal phase lock loop. What is going to happen if I put a division by n in the feedback path? Will this loop also work? Of course, this loop will work. I mean, it has the same dynamics as before. It is just that effectively, instead of having k by s, you now have got k by n by s, right. Some gain is there, 1 by n gain is there in the loop. So, you just have to work your way for that 1 by n gain, otherwise it will work. But the question is this: what is now going to be the relationship between phi out and phi ref? Is phi out going to track phi ref or something else is going to happen? Yeah. You see, whenever you have feedback, the idea is that this is the error signal, this is called the error, okay. And the job of the feedback loop is to make sure that this error is as small as possible, right. That is how you think of any feedback loop. You have got an error signal, the job of the feedback loop is to make sure the error is as small as possible, which means that these 2 points, one is phi ref, the other should be an estimate of phi ref. which means that phi out is now going to be equal to n times phi ref. Right. So, nothing drastic, it is just that phi out now has to be n times phi ref. What does that mean as far as the frequency goes? The phase is n times the reference phase, frequency is dou by d by dt of the phase is equal to the frequency. So, the frequency is n times the reference frequency, very interesting. Now, what is the constraint now on the loop bandwidth? We said that the loop bandwidth is constrained over here, right, to 1/10 of the oscillation frequency. Which oscillation frequency are we now talking about? Why did the loop bandwidth get constrained? The loop bandwidth got constrained because of this particular block. This block is not really there, it is not exactly like that, right. I do not have a plus minus over there, I have got two flip flops, they are giving me a digital output and the time for which it is 1 or minus 1 gives me the estimate of the error, phase error, right. So, there is an averaging that I am implicitly doing over there in my analysis, right. So, that is where the phase the bandwidth limitation of my control system came from. I mean this is where the analysis was incorrect, and because this analysis is incorrect, I can't arbitrarily increase the bandwidth, that is the story, all right. So, what frequency is this happening at? What is the oscillation frequency as far as this phase detector is concerned? The oscillation frequency is omega ref, right, which means that my loop bandwidth should be limited to 1/10 of omega ref, not 1/10 of omega out. All right. Now, how are you going to divide this phase? Is it possible to do such a thing? I mean, first of all, is this something interesting? Do you want to build this? Isn't this something interesting? Omega out is n times omega ref. I can have a reference frequency of 10 kilohertz, and if n is 1 million, I can generate 10 gigahertz. Right. So, it is something very interesting. I can use a low frequency as far as omega reference is concerned, but I can generate any high frequency as far as omega out is concerned. So, it seems like it is something which could have some utility. Now, how are you going to make this 1 by n? How are you going to divide phase? Is it possible to divide the phase of a signal? Now, the saving grace over here is that this signal, this phase is in the form of a digital clock. So, V out really looks like this. It is a digital clock, and is it possible to divide the phase of this clock. What does it mean when you say let us divide the phase of this clock? It means you also divide the frequency of the clock by a factor n. How do you divide the frequency of a clock? By using a counter. So, for example, a divide by 2 counter with one flip flop right, take the output from anywhere, take the Q output for example. So, this is the clock running at frequency f and this one will be running at f by 2. So, if I use this as my circuit over here, I am going to get and so on. Wonderful. So, I can use my knowledge of digital sequential circuits to build counters and that can help me in dividing a clock by n. Now, this n could be anything, n is 2, that is the example that I have drawn over here, n could be any number for all that you know, n could be a large number, right. You could conceivably have an adder, right, every clock cycle you add 1. So, let us say I have a register, I am just drawing a crude, very crude, this is not how it is done, okay. This is not how it is done. But anyway, I am still drawing it just to I could employ something like this, okay, and every time the register hits a value of n, whenever it hits a value of n, I am going to clear the register. Now, n can be programmable from outside and I have successfully divided which is the output clock over here. Well, the output clock could be the MSB of this. Something like this will work. Okay. It is just that this is not how it is done because of speed and other reasons. So, finally, this is not the implementation that we use, however, this is a crude possible circuit, right. You could use an adder whenever the result reaches n, you clear it, take the output from the MSB, right. That will successfully divide your input clock by a factor n. So, it is conceivable to divide your clock by an arbitrary number n. Now, only thing is n has got to be an integer, that is all. Okay. It is easy if n is an even number also, because otherwise you are going to have trouble in generating 50% duty cycle, but if n is an even number, then you can have 50% duty cycle comfortably. All right. So, that is basically the thought process. So, it is possible, it is conceivable to build such a clock divider. Now, let us just calm down, right. Let us calm down and think about what is going on over here. Let us say that we are dividing by 4, okay. Let us say n is 4, and let us say we are working with 1 hertz clock. F ref is 1 hertz, just for convenience. I want to see what the phase detector output looks like, etcetera, etcetera. So, as a function of time, as a function of time, let me first plot the reference frequency, the voltage, the reference voltage. So, the reference voltage probably looks like this. All right. Now, let us say that initially the VCO output is at 1 by 3 hertz. Let us say initially the VCO output was at 1 by 3 hertz, right. If the VCO output is at 1 by 3 hertz, then I am sorry, VCO output is 3 hertz, let us say. Okay, 3 hertz will be hard to show over here. Okay, I have got to change my scales. Sorry about the waste of time over here. Okay. Let us say that is my f ref, and the target output frequency is clearly 1 hertz, n is 4. However, let us say instead of 1 hertz, initially my VCO was giving little less than 1 hertz, maybe 0.6 hertz or something. let us say this is what the VCO was doing initially. Okay. It is running slower than required. Now, in that case, when I divide this by 4, there is a divide by 4 counter that I have got, and the divide by 4 counter, what it is going to do is it is going to count 2 cycles, then it is going to change its phase. All right. Now, what does this mean as far as the phase detector is concerned? It is not really V out by n, it is V out, the division is in the frequency domain. Okay. Right. So, what is going to happen to the output of the phase detector? So, this is running really slow, right. This is going to be compared with Vref. Vref is at a different frequency altogether, and the output of the phase detector is going to go to 1 at the plus 1 at the rising edge of Vref, and it is going to remain there till you get the rising edge of the other frequency, then it is going to come to 0. Immediately there is another rising edge of Vref, which means again it is going to go back to 1 and it is going to stay there forever till the next situation arises. Now, what does this mean as far as we are concerned? This means that the phase detector is telling you that, hey, you need to increase frequency, this is up, you need to go up in terms of frequency. So, the VCO responds and goes up in terms of frequency, because up signal is coming. Up signal is coming means that the control voltage is increasing. Now, if the control voltage increases, supposing the VCO responds to the control voltage in the correct direction, if it does not, then we have a problem, we have to invert the signs. So, the control voltage increases, and as a result the output of the VCO increases in terms of frequency. All right. Now, suppose the output of the VCO does not look like this, keeps going up in terms of frequency till it reaches, till it becomes faster, significantly faster. Suppose it now becomes 0.5 hertz. Okay, it is still not 1 hertz. In that case, what happens to the output of the counter? The output of the counter counts 2 cycles, then goes high, again counts 2 cycles, then goes low, etc. All right. So, once again the output of the phase detector goes up at this point of time, and then it comes down, but sure it comes down, and then again it goes up. and remains up for a very long time. So, you see that the phase detector is again telling you that you need to go up in terms of frequency, okay, increase frequency, become faster, speed up. All right. Now, suppose the VCO speeds up even further, and instead of 0.5 hertz, now it is running at 1 hertz, but with some funny phase alignment. It is not aligned to our reference. So, VCO is now running at 1 hertz. But I am going to put a lag of 180 degrees or so. Suppose this is how the VCO is running, in which case the divide by n is going to be something like this. Oh, I am sorry, I drew it incorrectly. So, it is going to count 2 cycles and then it is going to go up. All right. So, now you see that the frequency of V out by n and V ref are the same, however, there is a phase misalignment. Now, let us see what happens. So, what is going to happen is the output of the PD is going to go up, come down, then again it is going to go up and come down. And notice that now the output of the PD is on for a fraction of the time, is up for a fraction of the time, not permanently like before. Okay. So, when the frequency is different, when it is lower, up really goes high. Okay. Now, it is on for a fraction of the time. How much time is it on for? It is on for half a second out of every 4 seconds. So, for 1/8 of the time you have got up. Remember, I put a phase lag of pi degrees over here. Okay. Pi degrees typically corresponds to, it is half of 2 pi. So, half of 2 pi degrees is the phase error that I constructed. I put a lag of half of 2 pi degrees, 2 pi radians over there. Now, the phase is being divided by a factor of 4, which means over here I am getting a lag of 1/8 of 2 pi radians. 1/8 of 2 pi radians corresponds to a voltage of 1/8. 2 pi radians corresponds to a voltage of 1 as the PD output, right. So, that is what happens. So, the time average remains the same, it is 1/8, and I am only getting up pulses. Why am I getting up pulses? Because the output of the VCO is lagging behind by some radians. Okay. So, the output of the VCO needs to speed up, the VCO needs to speed up, it is lagging behind, right. So, eventually everything falls into place, and supposing this were the output of my clock divider, then my up and down signals would disappear altogether. So, the PD output would remain 0. Does it remain 0? Does it remain 0, or do you see something? Is the PD output 0? Well, recall that up and down of the phase detector are both going to be equal to 1 for a brief amount of time. If both the clock edges come together, where were we? Yeah. So, suppose Vref and Vout have their edges together. So, when both the clock edges come at the same time, plus 1 and both of these outputs, up and down outputs, become 1 at the same time. That means that after a delay, little bit of delay, the delay of the AND gate, the clear signal gets activated, and by the time the clear acts, you have got a little bit of delay. So, there is a short duration of time during which both up and down are high at the same time. Now, if you made the DAC over here, current steering DAC, up and down are high at the same time, it should not matter, up and down are high at the same time, fine, I 0 goes in, I 0 comes out, no charge accumulates on the capacitor. So, it is all clean. Unfortunately, this is not the case, right. Up and down are high together for a brief amount of time. Unfortunately, these two current sources I 0 and I 0 are never going to be exactly equal to each other. They are never going to be exactly equal to each other. What does that mean as far as we are concerned? That means that the output of the phase detector is going to see a brief pulse over here, both for up and down. Now, if the DAC was ideal, this pulse is irrelevant. Okay. Unfortunately, the DAC is not ideal. The currents will have some mismatch from each other. Now, if the currents have some mismatch from each other, let us say the up current is a little bit 1% more than the down current. That will mean that there is going to be a 1% charge accumulation on the capacitor. So, there is going to be so if I now look at V control is going to see a little glitch over here because of a little bit of charge accumulation on the capacitor. Is that understood? Is that understood? Why there is that little glitch over there? Okay. So, there is a little bit of glitch, V control is accumulating a little bit of charge, and at what frequency is this happening? Okay. First of all, how much charge is being accumulated? Let us say I have got I 0 plus delta I 0 and I 0 minus delta I 0. So, let us say these are the two currents that I have got, delta I 0 by 2. Okay. So, the mismatch between the up and down currents is delta I 0. All right. So, this delta I 0 is going through for what duration? The duration is the delay of my gate. This duration is the same every time, delta amount of time. Gate delay plus the delay for the clear to work. Okay. So, if you make that delay equal to 0, then once again it does not matter if the currents are mismatched. All right. So, this is the total amount of charge that is going in through this charge pump. All right. This charge of course, is going to get accumulated onto that capacitor, which means Q equal to C V, remember. So, the voltage that you get, the extra voltage that you get is this divided by the capacitance C plus C x. That is the extra voltage that you are getting. Fine. So, if this capacitor size is extremely large, then it should not matter, this delta voltage is close to 0. That is also true. Okay. Now, next is what is the frequency of this happening? At what frequency is this happening? What rate is this happening? What is the period of this non-ideality? What is the period? That is the period that I have got, from 2 seconds to 6 seconds. So, exactly 4 seconds, which happens to be the period of my reference. Okay. So, this glitch is happening at exactly the reference period. What does this mean? This means that if I look at the spectrum of V control, if I look at the spectrum of V control as a function of frequency, of course, V control, the final value should have been a constant voltage. That is what you wanted, a constant voltage over there. If you have a constant voltage as V control, then you are going to get a perfect frequency output of the VCO plus phase noise, but of course, let us ignore phase noise for now. Let us say that everything is noiseless, perfect. In which case, if V control is a constant voltage, then I will get a tone as far as the VCO is concerned. That is what I want. Unfortunately, V control is not a constant voltage. V control has some periodicity with frequency f. So, V control has a large DC component, which is what you wanted. It also has periodicity with repetition rate, f ref. Okay. It has all the harmonics. What does this mean as far as the output of your VCO is concerned? It is very straightforward. The output of the VCO will have all of these components in addition to the fundamental. So, the output of the VCO will be your n times f ref, impulse at n times f ref, but in addition to the impulse at n times f ref, see if the control voltage had been a perfect DC, then you would get this as the output. Now, I am saying it is not a perfect DC, it has all of these extra stuff in it, which means that you are going to get tones corresponding to those extra stuff around the carrier. Is this clear? What is the rate? Where are those tones going to come at? The tones are going to come at precisely n minus 1 times f ref, n plus 1 times f ref, etcetera, etcetera, n minus 2 times f ref, n plus 2 times f and so on. Right. So, these are the components that you are going to see at the output of the VCO. Now, the good news is that the bandwidth of the loop is a fraction of f ref, which means that within this bandwidth your output of it is a fraction of f ref. So, it is f ref by 10. In that bandwidth the output is going to mimic the reference oscillator. Outside that bandwidth whatever else could possibly happen is going to happen. This is what is going to happen. So, nothing is going to get filtered outside the bandwidth of the loop. All right. So, we are going to summarize all of this phenomenon. These are called spurs. Okay. So, in one word these are called spurs or spurious frequencies. So, whenever you have designed a frequency synthesizer like this, you are going to get all of these spurious frequencies. This frequency synthesizer has a name, it is called the integer n frequency synthesizer. Okay. Now, we are going to stop at this point of time and we are going to carry on from here in the next lecture. Okay. Thank you.